Hi everyone, it's me, Carolyn, and today's video is going to be about finding probabilities that don't fit in the empirical rule. So if you remember the last video, we talked about the empirical rule, and if you are remembering the normal curve is centered at the mean, and if you go one standard deviation up and one standard deviation down, we gather roughly 68% of our data. If we go two standard deviations down and two standard deviations up, we will gather 95. And then down three and up three, we gather 99.7% of our data. And then we did some manipulating and using the symmetry to break it into different sections. And as long as we were at those boundary values or those magic numbers, as I called them, we could calculate the probabilities. But of course, life is not all 1, 2, and 3 standard deviations away from the mean. So in this video, we're going to learn how to use technology. I do not use the table, but I will talk about how to use the table to actually find these probabilities. So first of all, we're going to just start with the standard normal. And the reason I know this is a standard normal is because I see a Z. So Z refers to our standard normal. And to remind us as well, the standard normal has a mean of 0 and a standard, and I'm going to abbreviate here, deviation equal to 1. So we need to kind of remember that. And if we were using a table, we could use the table to directly calculate these. And there are lots of tables out there out on the webs. You can find ones that are cumulative, or sometimes they just show you from like 0 to a value. So depending on what table you're using, you'll have to do different steps for calculating these probabilities. However, we're going to be using SALT in my class, and so I'm going to be using that explicitly to calculate these probabilities. And we will find that it is really quite simple. So I'm going to actually kind of walk through the problems first and get them set up. And then we'll go to SALT and I'll show you how to calculate them, and I'll bring these values back because I don't want to jump back and forth from this form to SALT every single question. So I'm going to set these up and then we'll go to SALT and get our values. So I like to always draw a picture just so that I can then relate it to kind of what the answer is going to be. So remembering that they are normal curves, and we are talking about the standard normal. So I always like to put my mean in the middle. And then we are looking for Z less than or equal to a negative 1.53. So negative would be smaller than the 0. I always just kind of put them in wherever. And this kind of sets up my boundary value. And I want to go smaller, so I'm going to shade to the left of that value. So there's kind of my picture. And I now go to SALT and actually pull the answer. I'm going to draw pictures for all of these so we can kind of see what we're going to look for. The nice thing about SALT is it also gives us a picture, and we can use it to kind of compare, did I put in the right things? So here I have less than or equal to 2.57. 2.57 is somewhere over here. How far up or how far down you draw it, it really doesn't matter. My picture is just for reference so that I can compare it to what I put into SALT to make sure that we're looking at the same space. So here again, we're looking Z less than or equal to, and we get something like that. I do want to point out again that we don't necessarily need less than or equal to. We could have had just strictly less than, because in a continuous model or a continuous variable, the probability of exactly 1 point is 0. So having that as a strict less than or less than or equal to does not matter. Here I'm going to be going greater than 2.16. Maybe I'll draw him on this side. I should have went every other so I could have fit them in. Again, we're still talking about the standard normal. I'm going greater than 2.16. So that gives me a value here. Other things I kind of look for when I'm getting my answers, this number is going to be a little bit small. It's going to be less than half because I have less than half of the graph shaded. This one's going to be more than 50%. This one's going to be less than 50%. The further out they are, the smaller it will be. And we saw that in the empirical rule on the last video, that anything bigger than 3 was really, really tiny. So bigger than 2 point something is going to be still quite small. So even though my pictures might not be scaled correctly, the answers will be. Again, my pictures are just for reference. So here I'm going to have a negative 1.53 or 58, sorry, and a 0.65. I probably should have drawn that closer to 0, but I wouldn't have been able to write the value in. And then this last one I have is from -1 to 1. I do this one specifically, and we'll probably do a couple more while we're in there. Whoops. Because this is one that we could answer using the empirical rule, because the empirical rule tells us that roughly 68% is between that 1 standard deviation down and 1 standard deviation up. So I should get an answer that is pretty close to 0.68. So again, I'm going to take these values. So we're going to be getting these values from SALT. So I'm going to switch where I'm sharing so that we can see SALT and how to use it. Okay, so in SALT, this is when I just click on my link to go to SALT. This is what I come up with. We will be using the distribution calculator because we are talking about our normal distribution. Things that we'll need to put in here is our mean. So right now we have a mean of 0 and a standard deviation of 1 because I am using the standard normal, the Z. I do have a left tail, a right tail, both tails, or between. Sometimes we will use both or any one of those. There's situations for all of those tails. Our first question asked for less than or equal to a -1.53. So that is a left tail, which is what I have clicked. And then I'm going to go into this box here and change that to 1.53. You'll see that shaded region kind of matched my picture. Theirs is going to be a little bit more accurate than my scaling, but that is okay. It also gives me my answer. So there's that 0.06301. So 0.06301. And I'm going to write that on our notes as well. Okay, the next problem is still a left tail, but we're changing that -1.53 to 2.57, 2.57. And you'll notice that we do get a lot bigger than 50%. We get 0.99492, 0.99492. One thing I wish that SALT had was a Z here, so maybe just a standard normal button. I understand why it doesn't, but that is okay. You'll also notice it does have a Z score down here. And of course, since we are working with the Z value I put in here is exactly the Z score because we are talking about the Z. Okay. Our next one, we did a greater than, so I'm going to have to switch my tail to a right tail. And we are going larger than 2.16, so 2.16. And we get our value of 0.01539. Okay. All right, this next one, we were going between two values, so I need to actually click the between button. And the two values I was going between is a -1.58 and a 0.65. 0.65. And we get 0.6851. 0.6851. All right. And the last one we had as an example was from -1 to 1, which we should get close to 68%. And so here we get that 0.68269, which is pretty close to 68%. If I rounded it just to the nearest whole percent, it is that 68%. I can quickly change here to go from -2 to 2, and I should get something that is close to 95. So there's my 0.9545. Again, it would round to 95%. If I go -3 to 3, I should see 99.7. There's my 99.73. The values that are shown on SALT are more accurate than the empirical rule, as the empirical rule does state roughly. Okay, I'm going to go back to our worksheet, back to my notes. And you can see that I have put those answers in as soon as it updates here. Okay, so there was our picture from -1.53. These were the values that we pulled off of SALT. And you'll notice here it was roughly 68%. We did get a 68.269%. Okay, so this is kind of how you would use SALT to do your standard normal, so working with Z. However, there are many different normal curves. They all have their own mean and their own standard deviation. So they are all over the place. Here are just a couple examples and pictures. Here's got a mean of 10. Remember, the mean tells you where you are centered. The standard deviation tells you how steep it is. The smaller the standard deviation, so there's our smallest one here, the steeper, more compact the curve will be. We can basically take any normal curve to our standard normal through this simple transformation, and that is the transformation of finding the z-score. Luckily for us, SALT, we do not have to find the z-scores, but if you were to use tables, you would need to find your z-score for all the boundary values and then use it to go to your standard normal table. So you would be calculating this z-score over and over and over again. And it is your data value minus your mean all over your standard deviation. So you can use tables and technology either to find these. I will be using SALT to help us do that. And what I'm going to do is I have one example with a couple of different set pieces, and we will set them up, and then we'll go to SALT, and then I'll come back and set the next one up because I only have 4. So we will do a little bit of back and forth on this situation. But I will have most of the pieces in here so we don't have to enter everything all of the time. Okay. Before I go and use SALT, I always make sure to read my question very carefully. I also like to draw pictures because then I can use my picture as a reference when I go to SALT to make sure that I entered things in correctly. So this one tells us that the life expectancy of LED light bulbs tends to follow a normal distribution. That tells me that little piece right here allows me to draw a normal curve. It has a mean of 50,000 hours. So that tells me where my center is. The standard deviation is something that would tell me how steep it is. With a standard deviation that large, it's going to be very, very flat. However, mine always look the same. Okay, so when I draw my curves, I know it's a normal curve, so I'm going to draw a bell. I put in my mean. So the mean is going to be that middle, that 50,000. And I put that in there for reference so that I can then, when I go and answer my question, I kind of know what side of the mean that value is going to be on. And then when I shade, I can kind of determine, is that number going to be bigger than 50%, smaller than 50%? If I'm doing a between That gets a little bit harder to determine, but if it's a one direction piece, I usually can tell at that point, am I bigger than 50% or smaller than 50%? That way, when I get an answer from my technology, I can determine if I'm close, if I'm in the right ballpark. Okay, so what is the probability that a light bulb will last less than 45,000 hours? So 45,000 is on this side of 50. And we are going less. So that would be smaller. So that means I'm going to shade in that direction. Okay. And now I've got my picture. So I'm going to go to salt and I'm going to let it do all of the hard work for me. So we're going to go into salt. Okay. And we are doing a left tail. So I'm going to put a left tail here. My mean is no longer 0 like it was earlier. My mean is at 50,000. So we want to make sure to get 50,000 in there. I kind of wish it would put commas in so I could see the commas. I also have a standard deviation of 4,500, so only 2 zeros. Okay. And we want to know less than 1,200,000. Notice I kind of compare my picture to the picture salt gives me. So then like, yep, it's on the left side of the mean. My answer should be smaller than a half. My answer is that 0.13326 is the answer, and that I'm getting from here. I wrote it down on my notes. I also know here this Z value. So if I would have gone through the data value minus the mean, so taking 45,000 minus the 50,000 divided by the standard deviation of 4,500, I would have gotten a negative, because it's smaller, 1.111. So you can think about on the 0, 1, 2, 3, and the -1, -2, -3, where about this value falls. So you can kind of get a feeling for that 68, 95, or kind of be past the 68 into the 95, and you can kind of then get a judgment as to where that percentage lies or that probability lies. So I use that also to kind of make all these connections for me. Okay, I'm going to go back and get our next one. So we'll go back to find our next question here. Give me a moment. Okay, let this update. Takes a little while for it to switch. There's the answer we'd gotten from this piece here. Notice it was quite a bit less than the 0.15. If I had pulled out my old table with the 68, 95%, I think we were kind of in the correct tail. So you can also use that to kind of judge as to what your answers would be, because we had that 0.15%, that 2.35%, all those other values as well. Okay. This question here says, if a company has 10,000 light bulbs, how many of them would you expect to last 45? Oh, so this isn't asking a probability. This is saying, okay, I have 10,000 light bulbs in this store. How many of them would I expect to last less than the 45,000 hours? Well, this is the probability that they last. Another way to interpret it is that 13.326% of all light bulbs last less than 45,000 hours. So basically, we're saying we want to know what is 13.326% of that 10,000. Of the 10,000. The word of tells me to multiply. So I'm going to put this in its decimal form, and we're going to multiply it by my 10,000. And we will get 1,332.6. So that's how many of those 10,000 should last that long. Okay. Here's another question then. What is the probability that a light bulb will last between 40,000 and 62,000? So again, I draw a picture. I left a lot of space on my notes to draw my picture. So again, the mean is in the middle. So my 50,000 is in the middle. 40,000 is on this side somewhere. It might be further away as opposed to where my curve is. That's okay. We use it just for reference. 62 is on this side. And we're going between those two. Okay. Again, I'm going to use SALT. If I was using a table, I would calculate the z-score for both of those values and then use the table to find the areas and then do some manipulating. Sometimes you would add, sometimes subtracting, depending on the table that you are using. But I would need to get the z-score for both of those. Lucky for us, though, there is a lot of technology out there. And the one I'm using is SALT, which is a Cengage product. Cengage does have it attached to a lot of their stats textbooks, which is one that I'm using for the course that I am teaching. So my mean again is still 50,000 and I still have that standard deviation, but we are doing between. So the first thing I'm going to do is change my button to showing a between, and we are going between 40,000 and 62,000. 62, 1, 2, 3. Okay. And there's my picture. Notice my picture was a little off. I should have gone further out, but that's okay. It does give me the probability right there, which can also be thought of as a percentage, the percentage of light bulbs that fall in this area. It does give me the two z-scores for those values. So we are between the 2 and the 3 in both directions. So we are past that 95, getting pretty darn close to that 99.7. You'll notice that in our answer. Our answer was a 0.98304. If I'd gone -3 to 3, we would have been at 99.7. Here we're only at a -2.2 to 2.6. So we didn't quite get there, but we're pretty close. Okay. Going back to our problems. Oops, wrong button. And I have one more to do, one more example for us. So first thing we'll do is we will let this update. So here was my -2.222 and a 2.667. I think those were the digits. So again, close to that 99.7 or that 0.9973 if we had used SALT. All right, one last problem for this video anyway. Okay, we're still using the light bulb problem, so still that 50,000 in the middle. Again, this information is not true. I do not know the normality of LED light bulbs. I do not know the mean. I do not know the standard deviation. I make these problems up or I borrow them from textbooks. Maybe I change the values a little bit, but it is just for illustration purposes only. So we are going to find the probability that a light bulb is going to last longer than 58,000. So again, 50,000 in the middle. The 4,500 is telling me how steep or flat the curve is. And then we're going 58,000. And we want to go longer. So that means more time. So that's this upper tail. Sometimes you will hear people call this an upper tail, a right tail, and so forth. The bottom one could be a left tail or a lower tail. Really depends, and it's just a way to describe which way that tail or that shading is going. And to find our answer, we once again go back to SALT. getting tired of going back and forth, but it's just the way things are. So again, we're still using our 50,000 and the 4,500. We are doing a right tail. You'll notice it switched to above, and we are going bigger than 58. Okay, I also look at my picture to see, yes, I was above. It is a little bitty piece. I should get something smaller than a half. I got something a lot less than a half. So 0.03772. You'll also see the z-score is 1.77, so kind of close to that 1 and 2. You'll also notice on the curves in your picture that it also shows you in the picture where it is in reference to that 1 and 2 and 3 and the -1, -2, and -3. I really like that idea to help you make those connections and kind of remembering the 68, the 95, and the 99.7. So I do appreciate Salt's and Cengage's pictures and idea with their technology to make all those connections for us. I'm going to go back for the last time to our example because I did write the answer in there. Once it updates, you'll see the answer pop in there. There it is. And it's 0.03772. And that is my last answer for finding probabilities of just normal curves using technology. In the past, and it wasn't all that long ago, technology is really a new thing when it comes to statistics. People were using tables, so these problems took a lot longer to do because you would need to find the z-score for this and then look it up on a table and then possibly manipulate it depending on what the table gave you. So I hope you enjoyed this video and I hope to see you in the next video. Have a great day.